So as usual, we can start by looking at the homework problems. So I think there were some problems kind of from the previous set that we hadn't gotten to before. So let's get to the beginning of those,
Okay.
if you have them marked.
Yeah, everything in red is what I redid or
Okay,
did that
let's see
I
where we are.
had a couple questions there that I was trying to figure out, but I guess we'll just start in on the ones that I did not do.
Okay,
That red one right in the middle, I
okay.
guess.
Okay, so for this problem, what role does the alkene play in the first step?
A base,
Good. Is it a strong or a weak base?
weak base.
But the sulfuric acid is a strong acid. So we know we're going to
Yeah,
start with an acid-base reaction. Good. Okay, and then in the second step, what role is the oxygen playing?
nucleophile.
And why is that reasonable?
There's a carbocation for a good electrophile. I guess it plays the role of nucleophile because it has a lone pair of electrons.
That's right. So we have to explain why each thing is playing its role separately. We have to know why the oxygen is a nucleophile, and why were you saying the carbon was an electrophile?
It has a positive charge.
Good. So that was a
It's carbo
nucleophile-electrophile reaction. And then in the next step, what type of reaction occurred in the next step?
an acid base.
So we saw that generally we alternate between nucleophile, electrophile, and acid-base reactions. Okay. Actually, I mentioned to you that all the reactions that we've been looking at, there's only one nucleophile-electrophile reaction, and that's when we have this alternating pattern. In the second semester, you're also going to see some reactions with two nucleophile-electrophile reactions, and then the pattern is more complicated. Then you don't really alternate so clearly between acid-base and nucleophile-electrophile, but all the reactions we've seen fall into this pattern of alternating. Okay, did you say you had a question about that one? It looks like you got that correct.
Is the alkene a better nucleophile than H2O or an alcohol?
That's a good point. Now, in this particular problem, H2O, oh, so you're looking at the previous one too. Okay,
Yeah.
so let's see. How should I answer that? Okay, that's an excellent question. That's good that you thought about that. In this case, it's probably not, there's probably no way to figure out just kind of from first principles who's going to get protonated, the alkene or the alcohol. But it turns out that the interesting reaction here occurs when the alkene is protonated first. So that's the preferable way to draw it out. So remember that we're not trying to draw everything that would happen in the beaker. We're just trying to draw the interesting things that happen that lead to further interesting reactions. So if you protonate the alcohol first, it turns out that there's not really any interesting reactions that can happen following on that. But if you protonate the alkene first, then the alcohol can attack it as a nucleophile. But that is something that you maybe would be hard to figure out from first principles. So in a sense, you kind of have to have maybe seen this reaction before. So I guess your answer to this is it's not that the alkene is a better nucleophile than the water. I don't know how to compare them. Neither of them are great. Neither
Okay.
of them are great nucleophiles. I guess maybe the alkene is. Maybe the alkene is a somewhat better nucleophile. But the important thing is when the alkene is protonated, that gives rise to a further interesting reaction. Whereas if the alcohol got protonated, there wouldn't be really any interesting reaction that would occur after that. So that's why this is the superior approach. But maybe, so to some extent this can be figured out, but to some extent we kind of have to memorize that the alkene is protonated here. So it's good that you were noticing that there was more than one possibility theoretically. That's good that you're thinking about that. I don't know, does that answer your question?
Yeah, I think that,
Okay.
I think that answers for
Okay,
now. And
good. Okay,
I,
so you did carry that out in the correct fashion. Good. Let's see.
great. And on, like, with those same um, cyclohexenes right there, I was kind of wondering, um, is the reason why the carbocation ends up on that tertiary carbon because it has 3 electron donating groups around it rather than the, say, carbon-6 landing there because it only would have 2?
Yeah, absolutely.
Okay.
So that really is just a normal application of what we've seen before. So why would you ask that question? Maybe it's because, so what type of carbon is carbon-1? Primary, secondary, or tertiary?
Tertiary.
Maybe the thing that was confusing you is that it's part of a ring. So it might be a little bit hard to determine what type of carbon it is, but it's still considered to be connected to 3 carbon chains. It's connected to carbon-6, carbon-7, and carbon-2. And each of those can donate electrons to it. So you can still apply those ideas of primary, secondary, and tertiary even when a carbon is in a ring.
Okay. And it would preferably land on that tertiary carbon rather than the carbocation end up on carbon-6, because that's only a secondary. Is that pretty...
Yes, exactly.
Safe to say?
Yeah,
okay.
That's right. But yeah, so the thing to keep in mind is, so that's just an application of something we've already seen in many earlier examples. So the same principles that apply to straight chains also apply to rings.
Okay, perfect.
Yeah. Good. Yeah. So so what you said was correct.
Thanks.
Okay. Okay, so this next example looks correct. What role did carbon-3 play in the next example?
Nucleophile.
What makes that reasonable?
It has a negative charge on it.
That's right. What role did carbon-6 play?
Carbon-6 was an electrophile.
Good. And what makes that reasonable?
It was attached to a halogen.
Why does that make it electrophilic?
Because of the delta positive charge on it?
That's right. It's probably always best to try to take things back to the charges. So the delta positive makes carbon-6 electrophilic. And what role did the iodine play?
Leaving group?
And we know that that's a good leaving group. All right. Actually, well, I guess so. Yeah, it has a small delta positive and it's attached to a good leaving group. So as you said, the key here is that it's attached to an iodine. That is a perfectly good way to look at it. Okay, and you actually drew the alkene as linear, so that's good. Looks like you. Okay, good. Okay, so those are good so far. Okay. By the way, notice that last reaction was only just one thing. No acid-base reactions, just nucleophile, electrophile. How did you know you could probably stop after just one step?
It didn't have any charges.
The main molecule didn't have any charges. Okay, good. Okay, so let's continue.
Okay. So it's kind of a long problem.
Let's see. Okay, you knew that you had to start with an acid-base reaction because there was a strong acid.
Yeah.
What role does carbon-1 play in the second step? In the second step, what role does carbon-1 play?
Electrophile.
And why is that reasonable?
It is connected to a positively charged oxygen.
Good. So we've seen that positive charges usually make the attached atom into the electrophile, and that's what's happening there. Okay, that looks good. That was correct.
Okay, so that looks good?
Yes.
Okay, I think I had a question on that.
All right.
How do we know the carbonyl oxygen is a better nucleophile than the alcohol? And I guess it's similar to what we were talking about before.
Yeah, so suppose that we had protonated the alcohol. If you protonate the alcohol, well, let's look at it this way. So here we protonated the carbonyl.
Mm-hmm.
What was the point of protonating the carbonyl? How did that help the second step?
It made that molecule have a better electrophile and leaving group.
Good. So it made the carbonyl into a better electrophile. Good.
Yeah.
And then what role did the alcohol play?
Nucleophile.
Good. So by protonating the carbonyl, we made it into a better what?
Better electrophile.
Good. Now, on the other hand, suppose that we had protonated the alcohol, as you were suggesting. If we protonate the alcohol first, that would make the alcohol into a better what?
Leaving group.
Good. And it would have a better electrophile then.
Yeah.
So then we would need something to play the role of nucleophile.
Uh-huh.
So is there anyone here that could have been the nucleophile to attack the protonated alcohol?
The oxygen on the carbonyl.
Now, do carbonyl oxygens often play the role of nucleophiles? Do carbonyl oxygens often play the role of nucleophiles?
I'm sorry, were you asking something different?
I'm sorry, I just repeated the same question twice because it was a little bit long. I was asking whether a carbonyl oxygen often plays the role of a what role do carbonyl oxygens tend to play?
Base.
Weak base, good. Do they play the role of nucleophiles often?
Not often. I think maybe you did address that in the past.
Maybe we haven't. So that's something we talked about before that we maybe haven't reviewed very much. So carbonyl oxygens look like they're nucleophilic because they have a lone pair. But what we discussed before, we haven't really reviewed this very much, but we've discussed carbonyl oxygens, even though they have lone pairs, are almost never nucleophiles. Okay. Even though carbonyl oxygens have lone pairs, they're almost never nucleophiles. That's not obvious, so that's something, just a fact that is helpful to be memorized. There might be some reactions where they're nucleophiles, but they don't come up in the introductory course. So in your introductory course, and on the DAT, you're pretty much never going to see a carbonyl oxygen act like a nucleophile.
Okay, that sounds good.
So do you see why it wouldn't make much point to protonate the alcohol? Because if we protonated the alcohol, what role would the alcohol play?
Electrophile.
And then it would have to react with something that was playing what role?
A nucleophile.
But there really aren't any good nucleophiles to attack it, because the carbonyl oxygen rarely plays the role of a nucleophile. So basically this is kind of confirming that what you said off to the left was correct. The reason we protonate the carbonyl first is because it gives rise to the interesting reaction. Whereas if we had protonated the alcohol, that would not give rise to an interesting reaction. So what your speculation on the left turned out to be correct. We want to protonate the carbonyl because that gives rise to the more interesting reaction. Now, as time goes on, rather than figuring this out from scratch every time, you probably just want to memorize what happens when you have a carbonyl around a strong acid.
Looks like it turns into an alcohol.
Right. I guess what I was going for is that when you have a carbonyl around a strong acid, the strong acid will protonate the carbonyl oxygen, not the other things in the reaction. When you have a strong acid around a carbonyl oxygen, it's the carbonyl oxygen that gets protonated, not the other things that might be around in the reaction. After you've seen that a few times, you get more comfortable with it. But the reason why that's true is because protonating the carbonyl oxygen makes the carbonyl want to play the role of electrophile, and then we get an interesting reaction. Whereas usually if we protonate something else, we don't get an interesting reaction. Okay, so that was a good question that you had. It's good that you were noticing there was more than one possibility. It's good that you were noticing there's more than one possibility. So in the beaker, both things will happen. In the beaker, sometimes the carbonyl will get protonated and sometimes the alcohol will get protonated. But it's the only one that's worth drawing is when the carbonyl gets protonated, because that's the only one that leads to an interesting reaction. So it's kind of a subtle point, but you drew it correctly, and what you said off to the left was correct. We're doing it this way because this is what leads to the interesting reaction. But in the long term, it's good to just memorize that if there's a carbonyl in the presence of a strong acid, it's the carbonyl that's going to get protonated, not the other things. So as usual, organic chemistry is kind of a mix of understanding and also memorization. We can partly understand why this makes sense, but it's also good to memorize what happens in this kind of case.
Okay.
Okay.
Yeah, thanks for explaining that.
So what role does a carbonyl oxygen tend to play in reactions?
The oxygen on a carbonyl would tend to play the role of base.
Good. Weak base. Would it be a nucleophile?
Not in a beginning course.
Yeah, that's right. Good. So we can just say no. That's right. Yeah.
No.
So for our purposes, it's not going to be nucleophilic. Okay. Okay, good. So, so that was a good question. It's good that you're thinking about these rather than just doing these mechanically. So that's the answer to the question. And like you said, this just gives us the more interesting reaction. Okay, so let's continue.
Okay.
Okay. So what role is the neutral oxygen playing in the second step?
The neutral oxygen in the second step, meaning, um,
The water oxygen, what role is that playing?
oh, over here. Okay, sorry. That was playing the role of nucleophile.
Why did you use that as the nucleophile instead of using the hydrogen sulfate? Because that has a negative charge.
We determined that because of resonance, that will basically be a spectator ion.
Yes, so does the resonance make it stable or unstable?
Very stable.
Does that make it reactive or unreactive?
Very unreactive.
So as you said, it'll be like a spectator. That's right. Excellent. So that's just a review of what we've seen before. Good. So it looks like that's looking good. I guess we can scroll to the right a bit. Okay, perfect. So that's exactly the right way to write that out. Good.
Okay.
Okay, excellent. Whoops, sorry. One moment.
Sorry.
Okay, now we can scroll to the right. Now, good. Do you notice that the product here was pretty much identical to the product from the previous reaction?
Yeah.
That shouldn't surprise us because we know what does H3O plus really mean? It just means acid and water. I think we discussed this last time. So I put these two problems next to each other. There's kind of a moral here, which is that these are really two ways of writing the same exact reaction. If we recall, we talked about that last time. H3O plus really just means a strong acid in water. So it gives us the same exact results as H2SO4 and H2O. And that's what we ended up with in this case. What's the solvent when you use H3O plus?
Water.
I think you had to take that into account because I think you used a second water molecule later on in the reaction. So you must have been assuming there was extra waters around.
Yeah.
So that's just a review of what we talked about earlier. Okay, good. So you did that correctly. By the way, in the well, no, we'll look at this new one. So let's see. So what role is carbon-2 playing in the second step?
Electrophile.
Good. So let's keep going. And why is it a reasonable electrophile?
Because it is attached to a positive atom, oxygen.
Great. And what role is the oxygen playing?
Leaving group.
That's right. And why is that reasonable?
It has a positive charge.
Okay, good. So let's scroll to the right. So here you use the alcohol solvent for the deprotonation step. Okay, that looks good.
Okay.
Great, good.
Great.
So how did the acid help this reaction? How did the acid help the nucleophile electrophile reaction?
It protonated the oxygen, making that molecule a better electrophile for the next nucleophile electrophile reaction.
Exactly. Yes. Good. All right. Now, why did you say the next reaction was no reaction?
They look just like two strong acids.
Do acids react with acids?
No.
No. What do acids want to react with?
Bases.
Okay. Excellent. So that's exactly right. So the good thing about your explanation is you were using the roles to explain it. That might seem obvious, but most students don't do that. So it's good that you're in the habit now of trying to use the roles to understand things. You said they're both acids, so they wouldn't want to react with each other. So that was a good explanation. Why did you say the next problem would be no reaction?
They're both bases, and they would not react with each other.
Good. What other roles could they play besides bases?
Nucleophiles.
But do nucleophiles react with other nucleophiles?
No, they would react only with electrophiles.
Right. So either way, it looks like no reaction. If you consider them nucleophiles, they wouldn't want to react with each other, and if you consider them bases, they still wouldn't want to react with each other. And why did you say no reaction in the third example?
For the same reason that they are both nucleophilic or basic.
That's right. Okay, excellent. So it's important to know when there won't be any reaction. Sometimes instructors test that directly, but the main reason it's important is because, remember, in most classes, you have to come up with your own syntheses where you decide what the reagents are. So you need to be able to consider what things will work and what things won't. So hopefully when you're coming up with a synthesis, you won't write down stuff like this. What doesn't make sense to try to put two bases together or two nucleophiles together. So you need to know when there would be no reaction. Okay, so those were good answers. That's good that you shifted gears there and saw that no reaction would occur. Good. Okay. Let's see. So this starting material looks a little bit different than the ones we've seen before.
Yeah.
So what role was carbon 1 playing? Well, what role did the nitrogen play in the first step?
Base.
That's right. What makes it a reasonable base?
The lone pair of electrons.
Good. Is it a strong or a weak base?
Weak base.
You know it's weak because it's just not in the list of strong bases that we've learned. So is the reaction really possible? Well, what type of role does H3O plus play?
Strong acid.
Strong acid. What makes it a strong acid?
The positive charge.
That's right. Pretty much anything with a positive charge is a strong acid. And then what role did carbon 1 play in the second step?
Electrophile.
Good. And was that reasonable?
It was attached to the positively charged atom, the nitrogen.
Right. So a lot of students would think that the oxygen should attack the nitrogen directly, but it doesn't work that way. Instead, the oxygen attacks the attached atom, as we've talked about that pattern before. So how did the acid help this reaction? How did that acid help the second step?
It made for a better electrophile in the original starting molecule.
Good. Okay, let's continue. So you did acid-base, then nucleophile electrophile, then you did another acid-base reaction.
Yeah.
Okay, excellent. So this is a reaction you might never have seen before with a kind of weird-looking starting material, but you were able to use the principles we've talked about to figure out the entire three-step reaction. So that's some good progress. That's 3 whole steps that you figured out all on your own. Hopefully that didn't seem super difficult, but most students would just kind of stare at this blankly. If we don't understand these rules, it's really hard to know where to get started with this. So that's a good application. Okay, good. So let's take a look at the next example. Okay, so here's an alkyne reaction. Good. So what role did the alkyne play in the first step?
Base.
Yeah, it's a weak base because of the carbon-carbon pi bond. You put the carbocation on carbon 2, presumably because that was secondary.
Yeah.
Okay, so this is kind of similar to the alkene reactions we've seen before. How did the acid make the second step easier?
It made the carbon 2 into a carbocation, which would make it a good electrophile.
That's right. The alkyne was not an electrophile, but with the positive charge, it turned into an electrophile. So that's what was the purpose of the acid. This reaction wouldn't have worked if you just had water attacking the alkyne. Okay, good. Then the next example.
Okay.
Okay, excellent. Oh, so actually let's scroll back up for a second.
Sure.
To compare these two examples. There's something interesting here. What role did the H3O plus play?
Strong acid.
Good. And what role did the HCl play?
Strong acid.
So how do you know? So if we want to make an alkyne into a better electrophile, what can we do?
Add an acid.
Right, but what acid should you use? Should you use H3O plus or should you use HCl? How do you know which acid to use? Well, if you want to make something into an electrophile that will be attacked by water, what acid should you use?
H3O plus.
Yes, you can see how that works in the first reaction. But if you want to make something into an electrophile that will be attacked by a halogen, what acid should you use?
HCl.
Or HBr, or HI. So again, remember what we're starting to try to do now is we're starting to try to figure out how you can come up with these reagents on your own. How could you have decided what's the right acid to use? Well, you want to use an acid that kind of also has the right nucleophile in it, if you see what I'm saying. If H3O plus doesn't just turn something into an electrophile, it also creates a water that can act like a nucleophile. And HCl doesn't just turn something into an electrophile, it also releases a chloride that can then act like a nucleophile. So now, hopefully, we can see that you could decide on your own which type of strong acid you want to use. You want to use a strong acid that will give rise to the nucleophile that you want to use. Okay.
Okay.
All right, so let's continue.
Okay, so this last example, we addressed it now, um, but we had said that the oxygen on a carbonyl will not act as a nucleophile, but it could act. Well, I guess the question was base, huh? Okay, so I did the problem two different ways.
Oh, I see. Okay. Okay,
And
that actually is good. You know, if you're not sure what's going to happen, it's great to do it both ways. So that actually is that's a very good idea. If you're not sure what's going to happen, don't just ponder it in your head, but do it two ways. That's great. So let me see what you wrote down. Let's see. Okay. So let's look at the first reaction that you did, the second step. Point to the second step of the first reaction so that I know we're looking at the same thing. Good. Now, you made a mistake in drawing the product from that. Take a look at the product you drew from that. See if you can find why that product is not correct based on the arrows. So the arrows you drew were correct, but we didn't draw the correct product based on the arrows. So let's examine that product.
I guess there's supposed to be an arrow right there.
Good. Good. But there's still a problem with the product that was drawn. So take your time and see. The arrows are correct. So point to the product so I know we're looking at the right place.
The product of the second step right
good.
here?
There's something wrong with that picture. That's not the correct picture for that product. So take your time and see if you can find the mistake there.
Oh, yeah. Okay, I see. Looks like there should be an H.
Okay, that's right. So that's important. Okay. All right. And then you deprotonated in the next step. So since we made a mistake there, the subsequent pictures will also have mistakes. So let's fix the rest of that. Okay. So who did you use as your base in the last step?
An oxygen off a carbonyl.
That's right. So that's fine. That's perfectly okay. Who else could you have used as the base? For that step. Who else? What's another basic atom around then?
You could have used this alcohol.
Yeah, that probably would be more conventional, but I don't think there's anything wrong with the way you drew it. So either of those would be fine. Also, presumably there's probably some extra solvent here that we didn't draw. You might just assume there's a water solvent and use that to do the deprotonation too. But I don't know, maybe not. So this is fine. So the way you did that is fine. Okay, so let's scroll back to the left. Let's see. Okay, so that first reaction is perfectly okay. And looking at the second approach, so let's scroll to the right. Okay, So it's really good here that you were drawing both possible approaches. It's really good to draw both possible approaches to see which one makes sense. But in both cases, we were a little sloppy about drawing the product, so we made a couple of mistakes. So
Okay.
point to the step where the water is attacking carbon 5. Good. Now point to the product from that step.
Oh, I forgot a little hydrogen there.
Right. So that means that our final product will be incorrect as well.
Yeah.
So those little
If-
things are important.
Yeah.
Now, one thing that's interesting to notice here is, so when we draw these correctly, do you notice you got the same product either way?
Yeah.
Okay. So if this was just to predict the products problem, it wouldn't really matter which way you did it. But which is the preferable mechanism? Well, which mechanism was simpler?
Well, they had the same number of steps,
Did
it looks
they?
like. Yeah, it looks like they each have one arrow to begin, and then they have a second arrow.
Careful.
And then
How many
third
steps
arrow.
were there in your first reaction?
Oh, you know what? Yeah, thanks. I forgot that arrow on both, actually.
That
So
makes
it
it
looks
easier to
like
count the steps. Good. So how many steps were there for the first reaction?
3 steps.
Good. And how many steps for the second reaction?
4 steps.
So that might make the first reaction seem like a better approach. More importantly, go back up to the first reaction. What type of step did we start with? Acid base or nucleophile electrophile?
Acid base.
Good. We had to because we started with a strong acid. And then what type of step was the second step?
Nucleophile, electrophile.
Good. And then what type of step was the third step?
Acid base.
So that just follows our normal pattern. But now
Yeah.
let's examine the four-step reaction. What type of reaction was the first step there?
Acid base.
And then how about the second step?
Nucleophile, electrophile.
And how about the third step?
Nucleophile, electrophile.
Notice how that kind of violates the pattern we've seen in the past, though. We don't usually do 2 nucleophile electrophile reactions in a row, right?
True.
What do
Yeah.
we usually do after a nucleophile electrophile reaction?
Acid base.
That's right. So that's something else that should have made you suspicious about that second pathway. The second pathway seemed maybe less reasonable because it's not following the same pattern that we've seen before. So that's something else that would have made you suspicious about that. Okay. But it is good that you thought to just draw it both ways. That's an excellent thought process. It's good that you didn't just ponder it in your head, but you actually drew both of those out. One thing that happened here, though, is because I think oftentimes when people aren't sure that they're doing the right thing, they get sloppy about drawing things correctly because they think, gee, this might not be right anyway. So I noticed on both of these we made some little mistakes in drawing the products. So it's great, if you're not sure what's going to happen, it's great to draw it out, but then you still have to be as careful as ever in drawing things correctly. Even if you're not sure that what you're writing is correct, you still have to make it as correct as possible. Okay, so now, those are all great. So we've seen some good things that we could use to prefer the top reaction to the bottom. It would be nice if there was a faster way to figure this out, though, so you didn't have to draw the whole thing out. So how could we see more clearly what's going to happen here? Well, basically, if you have a carbonyl and a strong acid, and you have some other things, who tends to get protonated? The carbonyl oxygen or the other things?
Carbonyl oxygen.
So that's a nice shortcut, isn't it? If you know that shortcut, then you don't have to work this whole thing out so laboriously. What role? So look at your second reaction. Point to the second step of your second reaction. That second step there. Good. What role is the carbonyl oxygen playing in that step?
Nucleophile.
Do carbonyl oxygens generally play the role of a nucleophile?
No, they don't.
That's something that we were reviewing again today. So that, again, would have been a faster way to reject that approach. Actually, you can kind of see why carbonyl oxygens don't tend to play the role of a nucleophile. Basically, when a neutral nucleophile attacks, it gets a positive charge, right? When a neutral nucleophile attacks, it gets a positive charge. And then it usually loses a proton to get rid of that positive charge, right? For example, look up in the previous example. What role did the alcohol oxygen play in the second step? What role did the alcohol-oxygen play in the second step? Yeah, the alcohol-oxygen on the left. That's still kind of maybe the carbonyl oxygen. What role did the alcohol-oxygen play?
It was the nucleophile.
Now, it started neutral. So what charge did it have after that step?
Positive.
And how did it get rid of the charge?
Deprotonation.
Good. So notice what generally happens to a neutral nucleophile after it attacks. It usually loses a proton to get rid of its positive charge. That's actually a very important idea that we haven't talked about before. That would be a good thing to have in your notes. What happens to a neutral nucleophile after it attacks? It loses a proton to get rid of its positive charge.
Okay.
So what happens to a neutral nucleophile after it attacks?
It usually loses its proton to get rid of a positive charge.
Good. Tell me when you have that down in your notes.
Okay.
Now, let's look at the carbonyl oxygen. Let's look at your second reaction down below. Point to the second step in that second reaction. What role is the carbonyl oxygen playing in that step?
Nucleophile.
Good. Now notice it started neutral. What usually happens to a neutral nucleophile after it attacks?
It would usually lose a proton
to get rid of the positive charge.
Yeah.
So now point to the picture where the oxygen has a positive charge. Notice this oxygen can't do that because it doesn't have a proton.
Yeah.
That's kind of the reason why carbonyl oxygens are usually not nucleophiles. Carbonyl oxygens are usually not nucleophiles because they can't get rid of the positive charge afterwards, so they don't attack in the first place. Remember, does nature like charges?
Nope.
So nature is not going to form a charge unless there's a way to get rid of that charge. That's kind of a problem-solving way to think about it. So generally, you're not going to form a charge that you can't get rid of, or that's not going to lead to an interesting or important product. So that's kind of the reason why carbonyl oxygens are usually not nucleophilic. They're not nucleophilic because they don't have a proton. So normally, neutral atoms usually can't be nucleophilic unless they have at least one proton to lose afterwards. We haven't talked about this before, but this is an important idea in organic chemistry. Neutral atoms are usually not going to be nucleophiles unless they have a proton to lose in the next step. Because if they don't have a proton, it's going to be difficult to get rid of the positive charge. With an acid-base reaction, which is what usually happens. So we kind of explained here why carbonyl oxygens are usually not nucleophilic, although you could just memorize that. So let's scroll a bit to the left. In any case, you were asking who would be the better nucleophile, the carbonyl or the alcohol. So who's the answer?
And I mean the alcohol definitely. I think I was.
Maybe you're thinking of the base. Yeah.
I got it confused, but
okay. So well, who would be the better base then? Or we shouldn't really think of it as the better base. I don't know who's better, but the point is, it's more interesting to use the carbonyl as the base because that's more likely to lead to the interesting reaction here.
Okay.
So the point is, if you have a choice between protonating an alcohol and protonating a carbonyl, which one should you protonate?
Carbonyl, oxygen.
So then the alcohol can act like a nucleophile. Because if you protonate the alcohol, the carbonyl is not going to be a good nucleophile.
Okay. Yeah.
Okay. All right. So it's so to try to summarize here, it's great that you drew out both possible approaches here. It's great that you drew out both possible approaches, and you ended up seeing that, in a sense, it doesn't matter which one you draw because you get the same product either way. We saw a bunch of reasons to prefer the first mechanism. However, in the long run, it's also better to have a much faster way to evaluate this. So the faster way to evaluate this is we should reject the second approach because it uses the carbonyl oxygen as a nucleophile. Carbonyl oxygens are generally not nucleophiles. Or an even faster approach, you don't even have to draw out that second approach. So we reject carbonyl oxygen as a nucleophile.
Okay.
The carbonyl oxygen is not a nucleophile. Okay, good. Now, And the even faster approach is just, if you have a choice between protonating a carbonyl and something else, who should you protonate?
Carbonyl.
Generally speaking, yeah. That would be much faster than all the things we talked about. So there's certainly long ways and short ways to figure stuff out in OChem. So that's the shortest way, so you wouldn't have to draw the second path out at all. Okay, so as usual, organic chemistry is a mix of understanding and memorization. It helps that we talked about this so we understand it thoroughly, but in the long run, there's some things that we can memorize that allow us to get through that faster. Okay, so anyway, so you had a good approach to trying to think this through by drawing out both paths. I think we talked that one to death, so we can keep going.
Okay,
so that's the end of that set. Let's go back up to the start of those reactions. Great. So point to the second reaction. Sorry, the second. Yeah. What role does the nitrogen play in that step?
Nucleophile.
And what formal charge does it start with?
Neutral.
What usually happens to a neutral nucleophile after it attacks?
It loses a proton to lose its positive charge.
Is that what happened?
Yeah.
Okay, so that just confirms the pattern. Let's take a look at the next reaction. What role did the water play in the next reaction?
Nucleophile.
What formal charge did the water start with?
It was neutral.
So what's probably going to happen to it in the next step?
Lose its proton and lose a positive charge.
And is that what happened?
Yeah. Yeah.
Okay, so now let's look at the next reaction. Who was the nucleophile in the next reaction?
It's alcohol.
And it started neutral, so what's probably going to happen to it after it attacks?
Lose its hydrogen or lose its proton to lose a positive charge.
Okay. And is that what happened?
Yeah. Yeah.
Okay, excellent. Let's look at the next example. Who was the nucleophile in the next example?
The chlorine
Excellent.
ion.
That's good that you found that. It was a step in, so that's good that you found that. Now, what formal charge did the chloride start with?
Negative.
So is it going to have to lose a proton?
Nope.
No. So notice the difference between negative nucleophiles and neutral nucleophiles. What happens to a neutral nucleophile after it attacks?
Usually it loses a proton so that it can lose positive charge.
Right. Negative nucleophiles don't have to do that, because what's the charge on a negative nucleophile after it attacks?
Neutral.
So it's already happy.
Yeah.
So it doesn't have to lose a proton. Okay, good. Let's zoom out a bit and look at some of the other reactions down below. Let's see. Let's keep going. Let's keep scrolling down. Let's keep scrolling. Whoops. Sorry, let's scroll up a bit. And let's keep scrolling down. Okay, well, that pretty much covers it. Anyway, I wanted to show you, so there's many examples of this on this page. You can see that there's many neutral nucleophiles on this page. And in every case, what happens to the neutral nucleophile after it attacks? It loses a proton. So that's something I probably should have mentioned before, because that turns out to be, might not seem very earth-shaking, but that turns out to be a very helpful principle in organic chemistry. So we want to make sure you have that in your notes. I find people have a hard time remembering that. So I'll pester you with it one more time. What happens to neutral nucleophiles after they attack?
They lose a proton so they can lose their positive charge.
That's right. It might not be apparent yet why that's so interesting, but as we go on, we'll see that. In fact, let's scroll back up to the beginning again. So point to the product of the second reaction. Point to the product of that second reaction. Good. Let's say this was a synthesis problem, and you were trying to make that molecule by introducing the nitrogen. You want to connect the nitrogen to carbon too. So you have to come up, so pretend that you can't see the starting materials on the left. If you pretend you can't see the starting materials on the left, what molecule would you need to use to attack carbon 2? To introduce that nitrogen?
Molecule you mean?
Yeah, you don't need to know the name, but what would be its formula?
I guess NH3.
That's right. But wait, if you're trying to make NH2, why do you have to use NH3?
Because it would need to lose a proton
Okay.
so that it can lose its positive charge.
So that's why that's so important for synthesis. That might not seem so exciting, but that's very important. Many people don't realize that if you're trying to make something with a neutral nucleophile, you have to imagine a starting material with one more proton than the product has.
Okay.
So that's how this is important for doing synthesis problems. If you're trying to make something with a neutral nucleophile, you have to ask, what would that thing look like with an extra proton? So let's point to the product of the next reaction. Point to the product of the next reaction. Good. Try not to look at the starting materials. So let's say we wanted to make that alcohol by attaching an oxygen to carbon-2. We want to make that alcohol by attaching an oxygen to carbon-2. What molecule should we use to bring in the oxygen? What would be its formula?
I think you would definitely use. You could use an H2O. I'm wondering if you could also use an OH minus.
That's an excellent answer. Excellent. Good. So there's really two possibilities. If you wanted to use a negative nucleophile, what would you use?
A negative nucleophile, OH minus.
Excellent. Good. But if you were going to use a neutral nucleophile, what would you use?
H2O.
Good. How do you know which one would work better? Well, that would require extra knowledge that we haven't talked about. So deciding which one would work better here would require some extra knowledge we haven't talked about. All we can say now here, those are the two possibilities. So here's the point, though. So notice, actually, the best way to do this is using H2O. By the way, what's the name of H2O?
Water.
Right. But wait, it doesn't look like H2O in the product. Why does it need two hydrogens if it doesn't have two hydrogens in the product?
After the nucleophile attacks, it will have a positive charge because it began neutrally, and it would then lose one of the protons so it could
That's right.
regain its neutral
Okay.
charge.
So the point here is, if you want to make something with a neutral nucleophile, you have to imagine what the thing would look like with one extra proton. And let's look at the next example as well. Point to the product from the next example. Good. That's what's called an ether, when you have an oxygen connected to two carbon chains. Let's say that we wanted to make that by attaching the oxygen to carbon-2. If we wanted to make that by attaching an oxygen to carbon-2, what would be what type of molecule would we have to use to bring in that oxygen that's going to attack carbon-2?
Alcohol?
That's right. Well, wait, it doesn't look like an alcohol in the product.
Right. It would need to lose a proton after having attacked.
So the point is, if you want to figure out what starting materials to use for a synthesis, if you're going to use a neutral nucleophile, you have to imagine the atom with one more proton so that it can lose it in the reaction. Okay, so that's why that's a really helpful idea to know that when a neutral nucleophile attacks, it loses a proton. That also allows you to work backwards. If you want to design a synthesis with a neutral nucleophile, you have to start with one more proton than you're going to have in the product. Okay, all right, so I guess so that's good enough for that set of problems, so we can move on to the next. Okay, chloride, bromide, and iodide are nucleophiles. Are chloride, bromide, and iodide bases?
No.
Generally not, because they're the conjugates of very strong acids. All right? What role does a carbonyl oxygen play in reactions?
That's a weak base.
Okay, so you can see what the point of that question was. So you can see why you had some. You can see why you weren't quite sure exactly what to draw on some of the previous steps, because we had forgotten that idea that carbonyl oxygens are generally not nucleophiles. That would have helped us out there. Okay, so do carbonyl oxygens generally play the role of nucleophile?
No.
So that would be an important one to mark. That was what was causing some of your confusion on the last step, because we had forgotten that idea. Okay? So does sodium hydride generally play the role of nucleophile?
No.
For question 4, no. How do you know? Well, you just know because I told you so. It's not really obvious. It looks like a nucleophile, but it generally just doesn't play that role. Again, organic chemistry is a mix of understanding, but also memorization. So why is sodium hydride not a nucleophile? Well, we just memorized that it's not generally a nucleophile. We didn't try to explain that. So some of these just have to be memorized. So that's good. O minus. Now, O minus is tricky. It can be either a strong base or a nucleophile. That's why, I don't know if you've noticed, but I've given you pretty much no problems with O minus. I haven't given you any problems with O minus because you wouldn't be able to tell whether it should be a base or a nucleophile. That requires more knowledge of OChem than we've gone over. So O minus is a very important reagent in organic chemistry, but it's too hard for us to do problems with it yet because O minus can go either way. O minus can be either a base or a nucleophile, and you have to learn more details about the specific reactions before you know what it's going to do. So we haven't done any examples with O minus, even though O minus is very important in OChem because we just haven't been ready for it yet. Okay, so that was a good answer. Sodium borohydride, nucleophile. Good. Is sodium borohydride a strong base?
No.
Why not? Well, we just memorized that it isn't. We just memorized that it's not a strong base. Lithium aluminum hydride, number 7, Grignard reagents, alkyl lithium, strong base in the presence of acid, otherwise nucleophile. Does it have to be good? Good. So that's a good answer. And that's kind of something that was partly figured out, but also partly memorized as well. So these three things, these questions 2, 3, 4, 5, 6, and 7, I think these are very important for your OChem career. So these are important things to make sure they don't get lost in your notes. One downside of doing a bunch of tutoring is people end up with so many volumes of notes that the important ideas can get lost. But these are some important ideas. You want to make sure these don't get lost. Some of these things we kind of have to memorize what roles they're going to play. So questions 2, 3, 4, 5, 6, and 7, these are all very important ideas that you want to keep reviewing. So number 3 we got wrong. Number 3 you were saying the carbonyl oxygen could be a nucleophile, but actually it generally doesn't do that. But the other ones were all correct. So the other ones you all got correct, so that's good. Okay, so let's take a look at number 8. Great. So this one I told you that the leaving group would fall off and then the nucleophile would attack. Good. Take a look at the starting material. Does that starting material have an acceptable leaving group?
No.
What can we do to give it a better leaving group?
Protonate it. Add an acid.
That's right. And what do you know? That's what we did. We added an acid. And then what happened after we protonated it?
It left.
As a leaving group. So you can see that reaction is extremely logical. We didn't start with a good leaving group, but by adding an acid, we made it a good leaving group, and then it left. Okay, good. What role did the sodium hydride play in the next reaction?
Base. Strong base.
Yeah. Does sodium hydride generally act like a nucleophile?
Nope.
No. How do you know? Well, we just memorized that. If we hadn't memorized that, it might be hard to know what would happen here. Good. Now, alcohols are nucleophiles, but they're not very good nucleophiles. How can we make an alcohol into a better nucleophile?
By adding a base.
And what do you know? That's what we did. And then what role did the oxygen play in the second step?
Nucleophile.
Just like we would have expected here. Okay,
yeah.
Good. So you can see, my point is I'm explaining that so that you can start to come up with these reagents on your own. You can say, gee, I want this to be a better nucleophile, so I need to add a base. Okay, good. Good. So we used a similar principle in the next reaction. What role does sodium hydride play in reactions?
Base. Strong
And that's
base.
what it did in the next reaction. And how does the base help the reaction?
It gives the starting reagent a better nucleophile.
Exactly, by giving it a negative charge. Very good. Okay. So I'm looking at the next reaction. So that next reaction is an ether. Does an ether have an acceptable leaving group?
Does the ether have an accept? No, it does not.
How could we give it a better leaving group?
By adding an acid.
And that's what we did. And then what role did the oxygen play in the second step?
leaving group.
Just like we would have expected. That was the whole point of the acid. Okay,
Yeah.
good. Okay, that looks good. This one looks like a repeat from before. But anyway, looks like you got that one correct. So, are alkenes electrophiles? Are alkenes electrophiles?
No, they would be nucleophiles or bases.
So how could we make an alkene electrophilic?
By adding an acid.
Good. By adding a strong acid.
Okay.
Good. But what strong acid should we use? How do we know what strong acid? So look at the last two examples on your screen. Notice that what was the strong acid we used in the first reaction?
Hydrobromic acid?
Yeah, or we can just say HBr, hydrobromic acid. Good. And what was the strong acid in the second reaction?
H2SO4.
So how would a chemist know which one to use? What's the difference? How would you know which one to use? When would you use the HBr and when would you use the H2SO4? Well, suppose that you want to add a halogen to the alkene. Which one would you use?
An acid that is based on a halogen.
Like HCl or HBr. You can see that happening in the first reaction. But suppose you want to add an alcohol to the alkene, well then you would use the second approach, right? So, so the point is, you use the if you want HBr is a good acid if you want to add a halogen because it provides the halogen too. On the other hand, if you want to use a alcohol, a good approach is to use H2SO4 plus the alcohol. Okay, and so then you did the remaining steps correctly there. Okay, that's fine. So let's continue. Yeah. So we can look at go to the right. I'll take another look. Yep, very good. That's all correct. Good. Well, here we have another strong acid. So how would you? So why are we using? So what's the difference between using H3O plus instead of using H2SO4 in an alcohol?
H3O plus would have water as the solvent and the nucleophile rather than the alcohol.
That's very well expressed. So that's good that you're using the names of the roles to describe it. That's right. So if we want alcohol to be the nucleophile, we can use H2SO4 plus an alcohol. But if we want water to be the nucleophile, we can use H3O plus. Although remember, H3O plus is basically the same thing as H2SO4 plus water. You could also put it that way. They're basically two ways of describing the same thing. Okay. All right, let's scroll to the right. Okay, good. So did you notice, so these last three questions were designed to be kind of similar to each other. If we scroll to the left again. So it's good to compare these and see three different types of attacks on the alkene. We used three, if you scroll up a little bit so we can have these on the screen at the same time. Well, we can't quite do it. But anyway, the point is we used three different combinations of strong acids plus nucleophiles. So we got three different results. So it's good to look at that to see what your options are when you're doing synthesis. So if you want to add a halogen to an alkene, how would you do it?
I use HCl or HBr or HI.
Great. If you want to add water to an alkene, how would you do it?
H3O plus.
Right. Or you could say H2SO4 and water. They're basically the same thing. Good. And how would you add an alcohol to an alkene?
I guess to have the alcohol be a nucleophile, it would be H2SO4 with an alcohol.
Yeah.
Again, the end it gives it ether. Is that right?
Oh, that's true. So when I say adding an alcohol, I didn't mean making it into an alcohol. I meant having an alcohol attack it.
I see. Okay.
After all, when we said that we were adding water to the alkene, we didn't mean we were turning the alkene into water. We meant that we had that water attack it. But yeah, it was a little bit ambiguous.
Sure.
That's right. So yeah, how could we have an alcohol attack an alkene?
By having the alcohol in solvent that's a strong acid like H2SO4.
Okay, excellent. Good. Okay, very good. So let's continue.
Okay.
Good. Let's scroll to the right. Okay. So I think that's a new reaction that you might never have seen before, that last reaction. Pretty complicated. I guess there was 4 steps in it. But you were able to work it out using the principles that we've talked about. So that's excellent. I did have to give you a little hint. I had to tell you that the leaving group would leave without being pushed. But once you had that hint, you were able to figure out the rest of it. Okay, good. So let's scroll back to the left. Good. So look at the starting material for that reaction we were just talking about. Did that starting material have an acceptable leaving group?
No.
So how could we give it a better leaving group?
Add an acid.
And that's what we did. And then what role did the oxygen play after we added the acid?
Leaving group.
Leaving group, just like we would expect. Good.
Okay.
Now take a look at the next example. Does that example have an acceptable leaving group at the start?
No, it doesn't.
So how can we give it an acceptable leaving group?
By adding an acid.
Right. And then what role did the oxygen play in the next step?
Leaving group.
Just like we would expect. Okay. And then I gave you the hint that told you the leaving group left without getting pushed.
Yeah.
This was a kind of complicated, weird-looking product, but it looks like you drew it correctly. Let's scroll to the right. Okay, we got kind of a complicated, weird-looking product you might not have seen before, but you followed the general rules and you figured that out correctly. So this reaction we're looking at here is one of the important reactions from the second semester. This is one of the important reactions. Actually, this is only the first half of it. This reaction actually continues on later. It does another nucleophile electrophile reaction, but this is the first half of it. Anyway, this is as much as we've learned how to do so far. So anyway, that's good. Let's scroll back to the left. Good. Next example. So, do you recognize what type of functional group is that compound with an OH?
Alcohol.
Good. Now, in that example, we decided to make the alcohol into an electrophile. Now, an electrophile has to have a leaving group. So how can we give the alcohol a better leaving group?
By adding an acid.
That's right, and that's what we did. And then what happened to the oxygen in the second step?
It was a leaving group.
Good. And then what role did carbon-2 play?
Electrophile.
So basically, by adding the acid, we eventually got carbon-2 to be an electrophile. So by adding the acid, we eventually got the alcohol to play the role of an electrophile. Now, did you notice the next example is also about an alcohol? The next example is also an alcohol, but in that case, we wanted to make the alcohol into a better nucleophile. How can we make an alcohol into a better nucleophile?
Adding a base.
And that's what we did. And then what role did the oxygen play in the second step?
Nucleophile.
Just like we would expect. So you can see there's 2 ways you can go with an alcohol. You can make it more electrophilic by adding an acid, or you can make it more nucleophilic by adding a base. Okay, let's see.
Okay.
So a lot of these examples I kind of tried to group together so we can see the patterns. So these 2 examples were trying to teach us something about alcohols. How can you make an alcohol more electrophilic?
Adding an acid.
And how can you make it more nucleophilic?
Adding a base.
Good. All right. Then the next example is an ether. How can you make an ether more electrophilic?
By adding an acid.
And that's exactly what we did there. Good. Then the next example with the HCl. Why did you put the positive charge on carbon-2 rather than on carbon-1?
Because the carbon-1 would have been a primary carbocation, and that's unacceptable. Carbon-2 is a tertiary carbocation.
Which is much better. Okay, good. Good. So, how can you get a halogen to attack an alkene? How can you get a halogen to nucleophilically attack an alkene?
by making it an acid, an acid HCl, HBr, or HI.
Yeah, so if you want to have a halogen nucleophilically attack an alkene, you can use HCl, HBr, or HI. How could you get water to attack an alkene?
By adding H3O plus.
And what do you know? That's what the next reaction is. The next reaction is for comparison. There we used H3O plus, and it was very similar to the previous reaction, but here we used water to attack. Good. Okay, great. Let's scroll down. Here's another example where we used sodium hydride as a base to make the alcohol more nucleophilic. That created what's called an epoxide. Okay, good, excellent. So let's continue. All right. So when the lithium aluminum hydride is in the presence of alcohol, what role does the lithium aluminum hydride play?
Strong base.
Good. Okay, and then you actually kind of went the extra mile. Then you did some more reactions that I wasn't really looking for here. But yeah, then the alcohol could attack the carbonyl. That's certainly reasonable. Could you continue more? Let's scroll to the right. Okay, all right. So those are certainly all possible reactions. That's right. The point here, though, is what role did the chemist probably want the lithium aluminum hydride to play?
Nucleophile.
That's what they're designed for. They're designed to be used as nucleophiles. So the point is that they didn't. Did they get the reaction they wanted here?
Nope.
No. Okay, so usually we wouldn't really bother tracing out the further steps here because we've already didn't get what we wanted. But actually, that's great that you thought about that some more. So there would be some more interesting reactions that could happen here. The O- could attack the carbonyl, so you would get that kind of interesting product there. So that's good that you traced this out some more. The most interesting thing about this is that we destroyed the lithium aluminum hydride, but that actually was a good process for figuring out what would happen after that. All right. Okay. Now, the sodium borohydride did not attack the alcohol because sodium borohydride is not a strong base. So instead, we got the reaction that was probably intended. Okay, good. And then in the next two examples, you have the Grignard or the alkyl lithium attacking the water because those are strong bases. Those are probably not the reactions that were intended there. And then there really isn't anything else interesting that could happen, probably then. Oh, well, actually, so if you'd wanted to, you could have gone further now and had the hydroxide attack the carbonyl, like you did earlier. But the point here is that we've already kind of done something that the chemist probably didn't intend. Okay, yeah. So good. So basically you saw what I was getting at here. So those were good answers. Those were good answers for those 4 questions. Very good. So let's scroll down. Okay, so in order to make these work better, you had to use non-protic solvents in the first step. You had to keep the strong bases away from OH bonds.
Yeah.
Good. Okay, now the way you wrote this out is correct. This would work. It's not quite the conventional way of showing it, though. Remember, what's the purpose of adding the alcohol in the second step? What do you want the alcohol to do? What role do you want the alcohol to play in the second step?
Acid.
Right. Now, is alcohol a strong acid?
No.
It's only a weak acid. Now, that's still probably good enough. But since our whole goal here is to get a protonation, we might as well go for overkill and just use H3O+.
Okay.
What you said, I think you would probably get full credit for what you said. I think it would work in the lab, but it's just not the way it's usually drawn in the textbooks. So even though what you wrote down is pretty much correct, let's write it the more like you would see in the textbook. So usually you would see in step 2 there H3O+. So what you said makes sense, but this is the more conventional way of doing it. And then again for the second reaction, what role did you want the water to play in the second reaction?
Acid as well.
Good. And it would do that. It's only a weak acid, but the O- is a strong base. But since we're going for it to be an acid, since that's the whole purpose, we may as well use a strong acid. Sometimes people show that as water, but it's a little more conventional to show it as H3O+. So again, your answer was not wrong. Your answer was not wrong. I think you would get full credit for it, but this is more how it's usually drawn in the textbooks. Okay, so let's scroll down. Now this reagent, I think you got a little confused when you were drawing the nucleophile.
Okay.
Because that isn't really a standard nucleophile. So you were trying to improve one of the reactions from up above. Which reaction from up above were you trying to fix?
Oh, I said Al. Okay, yeah, that's why. This is supposed to be lithium. That makes a difference.
Right, okay. What's the name of this type of reagent with the lithium?
Alkyl lithium?
Yeah, that's a logical name. Okay. All right, again, the way you wrote this is perfectly fine. Sometimes it's written this way in textbooks. It's a little bit more common, though, to write the second step as H3O+. So let's write it that way. But like I said, so you did make one mistake here by using the aluminum. Obviously, the aluminum is incorrect. But otherwise, you got all of those correct. Otherwise, your answers were correct. We just changed them to look a little bit more conventional. But the way you wrote them also made sense for each of those. Okay. So, good. Okay, good. Okay, so it's good that you took the time to do all of those problems, and I could see that you were doing them thoughtfully as well. There was a couple of problems where you considered more than one possibility and you drew out more than one possibility. That's good. That's good that you're taking the time to do those problems thoughtfully and think about whether there's more than one possibility in some of those. So I think that's very helpful practice. Let's go back to my screen. So it helps. Let's see. You ready to keep going?
Yeah.
Okay. It helps to consider whether a reaction is taking place under acidic conditions basic conditions or neutral conditions. You're under acidic conditions when you start with a strong acid. You're under basic conditions when you start with a strong base, even if it doesn't act like a base. If you start with a strong base, that's considered basic conditions. Even we know that things that can act like bases often can act like nucleophiles. But even if it acts like a nucleophile, if it could have been a strong base, that's considered basic conditions. And then neutral conditions are otherwise. No strong acid or strong base. Neutral conditions are when you don't start with a strong acid or base. And tell me when you have this written down.
Okay.
So what type of conditions are these? Acidic, basic, or neutral?
Acidic.
What type of conditions do we have in the first step?
Basic.
What type of conditions do we have once we add the second step?
Acidic.
What type of conditions do we have here?
Basic.
Because this is a strong base.
Yeah.
What type of conditions do we have here?
Neutral. Neither.
Because there's no strong acid or strong base.
Yeah.
What type of conditions do we have here?
Neutral. Oh, sorry. Oh, yeah, that's right. Well, the oxygen would have a negative charge. It's still a little gray in my mind, but I think that would act as a strong base.
So what role can an oxygen with a negative charge play?
It can either be a base or a nucleophile.
Is it a strong base?
I believe so. That's what I was trying to...
It is a strong base, yes. So negative oxygens can be either strong bases or nucleophiles. Okay. And remember, we kind of haven't been dealing with them much because it's hard to tell which role they're going to play. But remember, that's why I said it didn't matter up here. If you start with a strong base, it's basic conditions, even if it ends up acting like a nucleophile rather than a base.
Okay.
If it could act like a strong base, it's considered basic conditions. So could this act like a strong base?
Yeah.
So what type of conditions do we have?
Basic conditions.
Now, actually, in this reaction, this would actually act like a nucleophile, not a base. But it turns out that because it could act like a base, theoretically, it's still considered basic conditions. So what type of conditions are these?
Basic.
How do you know?
Because of the negatively charged oxygen.
Which is a strong base. Good.
Strong base, yeah.
Again, in this reaction, it might really act like a nucleophile, but because it theoretically could be a strong base, it's considered basic conditions.
Okay.
What type of charge do acids give to other things?
Positive.
Therefore, under acidic conditions, everything should be positive or neutral. Nothing will be negative. Except the conjugate of the acid. So for example, if you use hydrochloric acid, you're going to get chloride. Obviously, that's going to be negative because it's the conjugate of the acid. But everybody else in the mix has to be positive or neutral.
And that is just talking of starting materials?
That's throughout all the steps of the reaction.
Oh, okay.
Everything should be positive or neutral through all the steps of the reaction.
Okay.
Everything should be positive or neutral. This applies to all the steps of the mechanism, because they're all considered to take place under acidic conditions. Well, when something reacts with a base, what charge does the base give the other thing?
Typically negative.
That's right. So, under basic conditions, everything should be negative. Or neutral. Through all steps of the mechanism. There is one exception to that. Obviously, if you use this strong base, it has a positive spectator ion, so that can be positive. But besides the positive spectator ion, everything's going to be negative or neutral.
Okay.
On the other hand, under neutral conditions, the charges could be either positive, negative, or neutral. Okay, tell me when you have that written down.
Okay.
Okay, actually, so let's go back to your screen, and actually let's go back again to that last set of homework problems we were just looking at. So let's call up that last set of homework problems again.
Okay.
Great. And let's scroll up to the beginning of the reactions. Great. So let's look at the very first reaction. Is that under acidic conditions, basic conditions, or neutral conditions?
Acidic.
So what charges do we expect?
Positive or neutral?
Yeah. For everyone except the conjugate of the acid. Who's the conjugate of the HCl?
Chloride.
So that can be negative because otherwise it can't act like an acid. There's no way for it to act like an acid without the chloride becoming negative. But everybody else has to stay positive or neutral. So check. Is that what happened? Was everybody besides the chloride positive or neutral throughout all the steps?
Yeah.
So that confirms that we got that mechanism correct. So what we're going over now is another way to check that your mechanisms are correct.
Okay.
This is another way to check that your mechanisms are correct. You want to make sure the charges are consistent with the conditions. You want to make sure the charges are consistent with the conditions. So let's look at the second example. Is that second example, the second reaction, under acidic or basic or neutral conditions?
Basic.
Because of the sodium hydride.
Yeah.
So what charges do we expect?
Negative or neutral?
Right. Except, obviously, the spectator has to be positive. But besides that spectator sodium, everybody should be negative or neutral. Well, check the remaining steps. Is that consistent with the remaining steps? Was everyone negative or neutral?
Yeah.
Yeah. For example, the oxygen was negative, then the chloride was negative, and everybody else was neutral. If anybody had what would it mean if somebody was positive? Well, it would mean you messed up. If you had drawn anybody besides the sodium as being positive, you would have known you made a mistake, because that would not be consistent with your basic conditions. So this is a way to catch our mistakes. this will be helpful for the more difficult reactions in the second semester. So basically, at this point, I think you can handle just about most of the mechanisms from the first semester. But the second semester reactions, as I've said, can be more complicated, so we need some additional rules. So one thing that's helpful to make sure you're getting things right in the second semester is make sure that charges are consistent with the conditions. So let's take a look at the next example. What type of conditions is the next example in?
Also basic.
Good. So what charges do we expect?
Negative or neutral.
Right, except for the sodium. Well, were the charges consistent with that?
Yeah. Oops, I forgot
Yeah.
to write sodium. Or I guess
You don't have to write that. In fact, it's better not to write it because it's just the spectator. Okay. So they were consistent. What would it mean if somebody had a positive charge? It would have meant you messed up.
Yeah.
That would have not been consistent with the conditions. What type of conditions are the fourth example?
Acidic.
So what types of charges do we expect?
Positive or neutral except for the halogen.
Because that's the conjugate. Good. So were the charges consistent with that?
Yep.
What would it mean if somebody had been negative?
Something was wrong in the mechanism.
Yeah, it means you messed up. Good. What conditions do we have for the next reaction?
Also acidic.
So what charges do we expect?
Positive or neutral except for the conjugate of the acid.
And were we consistent with that?
Yep.
What would it mean if someone besides the bromine was negative?
Then I messed up.
That's right, but you didn't mess up. All right, let's scroll down and look at the next example. What conditions are the next example in?
The next example has acidic.
Good. So what charges do we expect?
Should all be positive or neutral.
Good. And are we consistent with that?
Yep.
Good. Now, of course, the hydrogen sulfate became negative, but that's okay because that's the conjugate of the acid. There's no way to avoid that. But besides that, everybody stayed neutral or positive. What would it mean if somebody else had been negative besides the hydrogen sulfate?
Then there was a mistake made.
That's right. So you can see we probably didn't make a mistake because the charges were consistent. Okay, so let's scroll down. Let's see. Let's keep going. Keep going. So let's take a look now at the example with the ring and the alcohol. Point to the example with the ring and the alcohol.
The ring and the...
Sorry. It's the kind of the third example on the page here now. Point to the third example on the page.
Oh, there it is.
There you go. Sorry. So what conditions is that taking place in?
That's basic.
Because of the sodium hydride. That's right. So what charges do we expect?
Negative or neutral.
And were the rest of your steps consistent with that?
Yeah.
What would it mean if you ended up with something positive?
Then the mechanism was written wrong.
That's right, but you did that correctly. Good. So let's keep scrolling down. Keep scrolling down. Okay. So what conditions do you have for the first reaction on the page here?
Basic.
That's right. So what charges do you expect?
Negative or neutral.
Good. And was your mechanism consistent with that?
Yeah.
Yeah, it was. Good. Okay, good. Good. What conditions do you have for the next reaction?
Neither.
Yeah, neutral. Because sodium borohydride is only a weak base. Good. So what charges could we have?
So you can have either positive or negative.
Or neutral, yeah. So under neutral conditions, there's really no restrictions on the charges.
Okay. So you said the sodium borohydride is a weak base. I guess, would that happen? Would it act as a weak base in any of the things we're looking at? I think we typically just...
So it theoretically could be a weak base, but we're really, all of these are intended to be used as nucleophiles. Okay. So if the reaction is set up correctly, it's generally going to act just like a nucleophile. But for example, you would not want to put in sodium borohydride with H3O+, because that would just destroy it.
Okay.
So sodium borohydride could act like a weak base, but generally it won't if you set up the reaction correctly.
Okay.
Okay? What conditions are we under for the third reaction?
For the third reaction, it's basic.
Good. So what charges do we expect?
Negative or neutral. And
Good.
it looks like it's all consistent.
Right. Except for the magnesium, which is kind of like the spectator metal in this case.
Sure.
Okay. Good. Let's scroll down. Okay. So what role? So let's look. Now we have some numbered steps. So what conditions are we under for the first numbered step?
Basic.
Even though the lithium aluminum hydride is not acting like a base. The lithium aluminum hydride is acting like a nucleophile now, but it could be a strong base, so it's still considered basic conditions. So what you said was correct. Good. So what charges do we expect?
Negative or neutral.
And is that what we got?
Yeah.
Yeah. Until step 2, then we change the conditions to what?
To acidic.
And then from that point on, the charges would be?
From that point on, I guess to follow that really would help have this be H3O plus.
Whoops. Let's see.
Well, I think we had looked
okay, so that's a good point. What you did originally, okay, I can't really use this because you didn't do the same mechanism. Good point. So if you use the alcohol, then you would basically be changing to neutral conditions. If you're using the alcohol, you'd be now under neutral conditions.
Yeah.
That whole reason we're using H3O plus is we want acidic conditions to make sure it's going to get protonated. Okay, well actually then these are not the best examples to use to illustrate this because you originally drew the mechanism using the alcohol. All right, so we won't talk about that more. I think you're getting the idea from that. Let's see. Okay, so good. Let's go back to my screen. Is this under acidic or basic conditions or neutral conditions?
Neutral.
Because there's no strong acids or strong bases. This is a weak base.
Yeah.
So what charges do we expect?
Any positive, negative, or neutral.
Yeah, it doesn't really put it on any restrictions. Okay. So what we just went over is a good way to check whether your mechanisms are correct. You can check whether your mechanisms are correct by asking whether you're getting results that are consistent with the conditions, by seeing if the charges are consistent with the conditions. That can be really helpful. One of the things that gives people the most trouble in OChem is knowing when to do their protonation and deprotonation steps. Often people do the acid-base steps at the wrong point in time. Well, one good way to check if you've done them at the wrong point in time is that they'll give you then the wrong charges. If you do the acid-base steps at the wrong point in the mechanism, then you'll usually get charges that are not consistent with your conditions, and then you can tell that you've made a mistake. All right. Do you have the reactivity handout that we've talked about before?
Yeah.
All right. You have that in front of you?
Yeah.
Good. Good. And we'll talk about it later. Okay, good. All right. So what's the definition of a nucleophile?
Nucleophile will donate electrons to join an electrophile.
What type of charge would make something a better nucleophile?
Negative.
Although there are also neutral nucleophiles. Good. How can you make something a better nucleophile? How can you make something a better nucleophile?
By adding a base.
Excellent. Good. What's another role in organic chemistry besides nucleophile?
Electrophile.
And what's the definition of an electrophile?
An electrophile will receive electrons to join a nucleophile.
How can we make something, so what type of charge would make something a better electrophile?
If it's a carbon atom, a positive charge. If it's any other, then a positive charge connected to it.
Excellent. So positive charges make things a better electrophiles, either if it's on the same atom or on the attached atom. That was a good answer. A positive charge makes something a better electrophile, sometimes by being on the same atom or sometimes by being on the attached atom. That was a good answer. So how can we make something a better electrophile?
By adding an acid.
By adding an acid. Yes. Good. What's another role besides nucleophile and electrophile?
Leaving group.
What's the definition of a leaving group?
Receives electrons to leave something.
So what type of charge would make something a better leaving group?
Positive.
Although some neutral things can be leaving groups. Good. So how can we make something a better leaving group?
By adding an acid.
Excellent. By adding an acid, we can give things better leaving groups. So what's another role besides nucleophile and electrophile and leaving group?
Base.
And what's the definition of a base?
Base will donate electrons to steal a proton.
Great. What type of charge would make something a better base?
Negative.
Good. Although there are some neutral things that are bases. Bases make other things into better whats?
Nucleophiles.
By giving them negative charges. Good.
Yeah.
So notice, charge is contagious. Charge is contagious. If you have a negative charge, what charge would you give other things?
Negative
That's
charge.
right. And if you have a positive charge, what charge would you give other things?
Positive charge.
That's right. Charge is contagious. So since bases tend to be negative, they make other things negative. And that makes them into better nucleophiles. Great.
It's like attitude.
That's right. That's right. How about, what's another role besides nucleophile, electrophile, leaving group, and base?
Acid.
What would be a good definition for an acid?
It will donate a proton and receive electrons.
Good. So what charge would make something a better acid?
Positive charge.
Although there are some neutral things that are acidic. So an acid makes something else into a better what?
Either electrophile or a leaving group.
Right. Oftentimes it gives a molecule a better electrophile and a better leaving group. Good. Because when an acid reacts with something, it gives the other thing what type of charge?
Positive.
Because charges are contagious. Okay, good. Excellent. That's excellent. So that was a very good recollection of the definitions of all of these. I find students have a really hard time remembering these definitions because they sound so similar to each other. So I know that must have taken some work to remember those. So that's good that you put in the work to carefully and clearly and quickly remember those. So I've been telling you, you have to know these definitions as well as a chess player knows how the pieces move in chess, and it looks like you pretty much do. So that's good that you put in the work to really carefully and completely learn those. If a chess player has to take 15 seconds to remember how a bishop moves, they can't really play chess. If it takes you 15 seconds to remember what a leaving group is, whether it donates or receives electrons, you can't really play organic chemistry. But you are answering all those questions very quickly in just a second or two. So that's good. That's good that you put in the time to really have crystal clear definitions of those in your mind. So that's very good progress. Good. So let's see. So I'd like you to draw some reasonable electron pushing arrows for this reaction on your screen.
Okay. Hmm. I think there'd be no reaction there.
And what was your thinking?
Because the chloride typically does not behave as a base.
That's a good point.
And there's not a good leaving group on the other molecule for it to behave like a nucleophile.
Excellent. That is exactly the right way to think about it. So the important thing is you're using the roles to think. Excellent. You're thinking in terms of roles. The chloride would not be basic. We've memorized that. It wants to be a nucleophile, but there's no acceptable leaving group in the other compound. So excellent. That was kind of a trick question, but you figured it out. Excellent. There would be no reaction. Okay, well, we're not just going to shut up the lab and go home for the day. We need to try to adjust this so we can get a reaction. So let's try to adjust these reagents so we can get the reaction that the chemist probably intended here. So what we need to do is let's try to make the alcohol into a better electrophile. So try to come up with some reagents that would accomplish what the chemist was probably trying to accomplish here, but failing. So what's the purpose of the acid?
To make the starting molecule be a better electrophile.
Okay, so let's draw the mechanism for the first step.
Okay. And in this case...
Now let me interrupt you for a second. How many charges should we change on every step of every mechanism?
Yeah, thanks.
Without that, we haven't really changed the charge. Okay, good. Now, does it look like this molecule is happy or unstable?
Unstable.
Now, I know that you've said that you're going to add NaCl, but that's not going to happen until the first set of reactions can't happen anymore. So we're going to add the H3O plus and then wait a minute before we add the NaCl. So are this reagents you have here now stable? Well, actually, now that I think about it, there isn't much more that could happen here. The water could attack, but that would just give you the same molecule you started with.
Sure.
All right.
Yeah.
Okay, so what do you think will happen next?
Well,
So there isn't really much more that can happen in step one.
True.
Because even if the water did attack, it would just give you another molecule of the same thing. So now what's going to happen in step two?
Well, you'd add the NaCl.
And what role will the chloride play?
Nucleophile.
Okay, so this would work. This would give us what the chemist was probably going for. However, one of the principles of synthesis is that we want the simplest synthesis with the fewest steps. So what you did here is first you added acid, and then you added the halogen separately. But we've actually discussed today, there's a way of adding an acid that adds the halogen at the same time.
Oh,
what
sure,
type of
yeah.
acid comes with halogen already as part of the package?
Like HCl.
That's
would
right.
work.
So, actually the way you wrote this actually might work okay. Well, let's see. Okay, yeah, so this reaction, there's some reasonable to this. You might end up getting some E1 reactions here. We haven't talked about that, but you might get some of that in this case. In any case, there's a much more direct way to get the desired outcome here. We don't need to do this in 2 steps. So let's erase that second line and try again. That was good thinking, but we can do this more simply and with a better yield by adding a better acid. That's right. And now let's draw the mechanism.
I guess that can stay.
Good. Great. And I'll give you a hint. In this particular reaction, the leaving group leaves without being pushed.
Oh, okay.
There's no reason you should have known that, but that's what happens here.
I think we did one of those before.
Right. Oh, I don't expect you to have those patterns memorized because I haven't really spelled them out. But anyway.
Great.
Notice, even if you didn't know the exact mechanism here, even if you didn't know the leaving group fell out first, you can still guess the correct product.
Sure.
Okay. Okay, so remember, what we're trying to do now is I think you've made excellent progress on figuring out the mechanism and predicting the products when you're given the starting materials. So the first thing we did is so if you remember in the tutoring, the first thing we did in the tutoring is I drew the arrows for you. And then you learned how to draw the product based on the arrows. So then we moved up to the next level of difficulty where you had to come up with the arrows yourself when you were given the starting materials. And I think you've learned how to do that. When you're given the starting materials, you now have good ways of drawing the arrows. So the next thing we have to learn how to do is how can you come up with the right starting materials? Because many problems in organic chemistry require you to provide the starting materials for a synthesis. So now we're moving up to the next level of difficulty. So we just learned here, we went over the right starting materials. We saw here that we needed an acid, but you have to choose the best acid. In this case, the best acid is HCl because it comes with the halogen already packed in. Okay, good. So that's good. I'll go back to my screen. So let's try to predict, try to come up with reasonable arrows for this on your screen.
Okay. Again, I think we won't have a reaction because that bromide would not act as a base, and it cannot act as a nucleophile because there is no good electrophile or leaving group.
Excellent. That's very good analysis. So let's try to come up with better starting materials than this chemist did. Let's say we did want the bromine to be a nucleophile. Let's try to come up with a way that the bromide could be a nucleophile.
Okay.
Great. In this case, we know that the leaving group can't just fall off. How do you know the leaving group can't just fall off here?
True. It would make it an unacceptable primary carbocation.
That's right. Okay, so let's continue.
Okay.
Okay, excellent. So this is pretty similar to the previous example. Why did you use HBr as the acid and not H3O+?
Because it was simpler.
Why is this simpler?
Well, if you only used H3O+, then you would have water be the nucleophile later.
Rather than the bromine. Good.
Yeah.
Okay. All right, very good. I'll go back to my screen. Let's predict the product for this reaction.
Okay. Okay, again, no reaction. The iodide would not play the role of a base, and there are no good electrophiles for it to play the role of nucleophile.
Right. There's really no chance of an acid-base reaction here because the molecule on the left isn't even a weak acid. Okay, so that was a good analysis. What role did the chemist probably want the iodide to play?
Nucleophile.
So let's try to fix this reaction so the iodide can play the role of a nucleophile by using better starting materials.
Let's see. Okay.
Okay, excellent. Good. So, so you use the HI here. Good. Why was the HI better than H3O+.
You wanted the I to act as a nucleophile.
That's right. So we want to use an acid that brings the halogen along with it, so to speak. Very good. All right, good. I'll go back to my screen. Let me introduce a new idea here. There's 3 different types of nucleophiles. There are good nucleophiles, there's poor nucleophiles, and then there are non-nucleophiles. I guess those aren't really a type of nucleophile, but anyway. The point is, there are good and poor nucleophiles. The poor nucleophiles have neutral oxygens. Pretty much most other nucleophiles go in the good nucleophile category,
Okay.
even if they're neutral.
Okay.
So what type of nucleophile is this?
A poor, or sorry, yeah, a poor nucleophile.
Because it has a neutral oxygen.
Yeah.
What type of nucleophile is this?
Also a poor nucleophile.
Because it has a neutral oxygen. What type of functional group is this?
Alcohol.
Right. What type of nucleophile is this?
A good nucleophile.
Even though it's neutral. Neutral atoms can be good nucleophiles as long as they're not oxygens.
Okay.
What type of nucleophile is this?
Good nucleophile.
Well, but wait, it's an oxygen. How can it be a good nucleophile?
The negative charge makes it.
Yeah,
good.
the most important factor in organic chemistry is the charges. It's only neutral oxygens that go in this poor nucleophile category. Of course, we know this could also be a strong base. Okay. Maybe we should explain why that is. Why are neutral oxygens really not that great as nucleophiles? Well, what's the definition of a nucleophile?
It donates electrons to join electrophiles.
So would it go at the head or the tail of an arrow?
The tail.
Now, what makes this a reasonable nucleophile? Why is it a nucleophile at all?
The lone pair of electrons.
But how electronegative is oxygen?
Quite electronegative.
So do you remember who's the most electronegative element in the periodic table?
Fluorine.
That's right. And how far is oxygen from fluorine?
They're neighbors.
It's only one step away.
Yeah.
Therefore, this oxygen is this oxygen is highly electronegative. Would that mean that it wants to hold on to its electrons or give them away?
Keep them.
Would that make it a better or worse nucleophile?
Worse.
That's the reason why it goes in this category of poor nucleophiles.
Okay.
Compare that with a nitrogen, Who's closer to fluorine, nitrogen or oxygen?
Oxygen.
So who wants electrons more?
The oxygen.
So who would be more willing to donate electrons?
Nitrogen.
So who's the better nucleophile?
Nitrogen.
Nitrogen. So that's why neutral nitrogens can be good nucleophiles, but neutral oxygens are poor nucleophiles. That's one of the important skills in OChem and on the DAT, comparing two things to decide who's the better nucleophile or electrophile or leaving group. Maybe we'll go into that in more detail later. But notice how we used their electronegativity to decide who would be the better nucleophile here. That's an important skill. Okay, so in general, neutral oxygens are poor nucleophiles. Generally, they can only attack things that are positive. They're not good enough nucleophiles to attack neutral molecules.
And that would include something like a strong acid, HCl, even though it's not technically positive.
I don't know if I quite followed that. Actually, I guess that wouldn't be quite true. That's a good point. That's a good point, because if it reacted with HCl, it wouldn't be acting like a nucleophile. It would be acting like a base.
I see, yeah.
And as a base, they can react with HCl.
Okay.
In fact, you've seen many examples of that already. We've seen many examples where neutral oxygens do react with HCl. So this is where it's helpful to distinguish between nucleophiles and bases. As a base, this can react with a neutral molecule, but not as a nucleophile. In fact, sometimes, even when it has a positive charge, even then sometimes the oxygen can attack. But it definitely needs the positive charge before it can attack. Okay. So what role do neutral oxygens play in reactions?
They would play a poor nucleophile.
Or what else?
Or they play the role of an acid or a base. Weak acid or weak base.
Yeah. In order to be an acid, they'd have to have a hydrogen connected to them. Okay.
True, yeah.
Okay, that's a good point. They can also play the role of weak base. And this could play the role of a weak acid. Okay. Good. Good point. Okay, let's see. So let's try to predict what would happen here. Try to draw reasonable electron pushing arrows on your screen.
All right. Well, I think it would not have a reaction because we said that this oxygen, being neutral, is a poor nucleophile that would only react with something that has a positive charge. And although this is a good leaving group, the bromine, there is no positive charge. So I would say no reaction.
Good. That's the right answer, and that was a very good, clear analysis. That's the exact right way to analyze it. Okay. So how can we get a reaction to happen here?
Well, we'd want there to be a positive charge somewhere, either, let's see. Is our goal to make the alcohol be a nucleophile attack?
So that's a good question. Really, that's the only thing we could do here. So let's say, so let's try to make the alcohol more nucleophilic. How can we make that? So just tell me in words, how would you make the alcohol more nucleophilic?
By adding a base.
That's right. Good. Can you think of any base that might work here?
Something like sodium hydride, perhaps?
Perfect. That is the exact, precise, exact right base. Good.
Okay. So if I added sodium hydride, I'm going to try splitting this up into steps. Well, I guess you don't need to.
Why don't we need to? What role does sodium hydride play?
Sodium hydride is a strong base.
Is it a nucleophile?
Nope, it's not.
That's why we don't need to keep it away from the bromide. We don't need to worry about the hydride attacking the bromide. That's why that was such a perfect choice. If we had used something that could be either a nucleophile or a base, we might want to keep the bromide away until it had already played the role that we want. So sodium hydride was a perfect choice here because it can only be a base. So there's no danger about putting it in at the same time as the bromide. We know it's not going to attack the bromide because it doesn't act like a nucleophile. How do we know it doesn't act like a nucleophile? Well, we just memorized that sodium hydride is always a base. So that was a very good choice for a base here. Good. Because remember, it's best when possible to do the synthesis in one step.
Okay, yeah.
Okay, so that's excellent. So let's continue.
Okay.
Okay, excellent. Very good. So if you scroll up a bit, now we can see two common patterns in OChem. Notice that up above, we showed how to make things into better electrophiles by using acids. And now we've seen how to make something into a better nucleophile by using a base. So those are some of the important principles that help you to come up with your own reagents if you're doing a synthesis problem. Good. I'll go back to my screen. So let's predict what would happen here. Let's try this on your screen.
Okay. Don't believe there would be any reaction there. In order for that alcohol to attack nucleophilically, I think we would want to add a base.
Good, because neutral oxygens are such poor nucleophiles, they can only attack things that are positive, and we don't have anything positive here. By the way, notice you can't fix this by adding an acid, because the acid is not going to attack the halogen side. You can't make the left-hand side of this positive by adding an acid in this case, because the left-hand side doesn't have a weak acid. So our only choice here is to try to make the alcohol more nucleophilic. So how can we do that? That's actually the same thing as we saw in the previous reaction. Okay, so what could we do here?
I think we'd add the same thing, the sodium hydride. Which would act as a base. Steal a proton, making the oxygen more nucleophilic with a negative charge, which could then...
Good. Don't forget to change two charges from the first step. Good.
And leave you with the
Great.
guide. And okay.
Excellent. So this was pretty similar to the previous reaction. Let's scroll to the left so we can compare them. Do you see these were almost the same thing? It's just in the previous reaction, if you scroll up a little bit more. In the previous reaction, the alcohol and the halogen were in two separate molecules. Whereas here, the alcohol and the halogen were in the same molecule. But notice in OChem, it doesn't really matter very much how many molecules you have. What matters is the functional groups. In both cases, we had an alcohol and a halogen. It didn't really matter whether they were in the same molecule or not. We got very similar reactions in both cases. So how do we make an alcohol into a better nucleophile?
By adding a base.
Right. Now, it can be tricky to figure out what's the best base to use. I'm not saying that you always use sodium hydride as the base. Actually, you kind of have to learn the base for each reaction as you go. So the bases oftentimes have to be memorized, or you have to learn new principles. So in this case, sodium hydride was a good base. Other reactions that require bases, you might use a different base. We haven't gone into that. But in this case, sodium hydride certainly worked well. All right, I'll go back to my screen.
Okay.
Okay, so let's predict what would happen here. Yeah, no reaction. Because what role does an alkene play in reactions?
Either a base or a nucleophile.
But the chloride is also a nucleophile, so they wouldn't want to react with each other. So let's try to fix these reagents so we can get a reaction.
Okay. So you could... get a reaction this way.
Excellent.
And that would leave you okay.
Perfect. Excellent. So, what was wrong with the first reaction? Well, what role do alkenes want to play?
Alkenes either want to be a weak base or a nucleophile.
Good. And what role does the chloride want to play?
It only wants to play nucleophile.
So we weren't getting any reaction because we had two nucleophiles. So clearly the solution is we had to make something into a better electrophile. Well, how can we make something into a better electrophile?
By adding an acid.
And that's exactly what you did. You solved the problem by adding an acid so that one of them would become electrophilic. The acid made the alkene into an electrophile, and then you were able to get the reaction. That was very good. I'll go back to my screen. Let's predict the product here.
Okay. The oxygen there would be a poor nucleophile. Alkene, you could have that be an acid.
Okay, so what role did the alkene play in the first step?
Base.
Good. And what role did the water play?
You know what? That wouldn't work because it's a weak base, and that would be a weak acid.
That's right. Okay. So that's good that you caught that. That's what I was going for there. That is a very common mistake that people make. You can't have a weak acid react with a weak base. So people often try to do something like that, but that won't work. You always have to make sure that one of them is strong.
Okay, yeah.
So that's an important habit to get into. Okay, so that's good that you had second thoughts about that problem. So notice it's not good enough to say that you have an acid and a base. You have to make sure that one of them is strong before you can get the reaction to happen. Okay, so that's an important habit to build. So actually there would be no reaction here so far. Good. So how can we fix this so we can get a reaction?
You'd want to add a base. Or an acid. I guess if you added an acid, you could do this. That way, you would have this reaction happen.
Why are you getting an acid-base reaction now when you couldn't get an acid-base reaction before?
Now we have a strong acid.
That's the key. Yeah. Water is not a strong acid, but H3O plus is a strong acid, so it can react with the alkene. Good.
Okay.
Be a little bit more careful with the products from that first step. Or no, actually, I'm sorry. Back up for a second. So let's not erase anything. What are your conditions? Is this reaction taking place under acidic, basic, or neutral conditions?
It is acidic. So there should not be a negative charge.
You should be pretty surprised if you see someone who's negative. Yeah. Okay.
So I would just do.
So we just misdrawn that. We left out one of the hydrogens. Okay.
Yeah.
Okay.
Okay, that makes more sense.
Yeah, you could do that. You could do that. That's not generally how these are drawn, though, in this case.
Okay.
What's the solvent for this reaction?
You could have H2O.
So that would be the more normal way to write this.
Okay.
What's the solvent when you use H3O+?
Water?
Yeah, that's not obvious, but H3O+ is just water plus a strong acid. So I think the way you wrote it before would probably be acceptable, but this is the more conventional way to draw it.
Okay. Then you'd have H3O+.
Okay, that one gave us a little bit of trouble. Anyway, if you scroll up, I wanted us to see the analogy between this reaction and the HCl reaction. Notice, why did you use a different acid than in this case? Because in the first case you wanted a halogen to be the nucleophile, and here you wanted water to be the nucleophile. Okay? Also, we reviewed the very important idea that you can't have an acid-base reaction unless at least one of them is strong.
True.
Let's predict the product for this reaction.
I think there'd be no reaction here again.
It's pretty similar to the water case.
Yeah.
So yeah, there's no reasonable reaction here. Neither of them is strong, so you couldn't have an acid-base reaction. So let's try to fix this so we can get the reaction the chemist was probably intending.
Okay.
So let's try to how could we make one of these more electrophilic?
By adding an acid.
So let's try doing that. Okay. Now, who do we want to be the nucleophile in this reaction?
The alcohol.
But who was your solvent from your first step?
Water.
That could be the nucleophile instead, which is not what we want. So H3O+ is not the best acid to use here because it would introduce water.
Okay.
Excellent.
And I guess you would just assume that it has an ether.
You could use an ether, but why not just put the alcohol in the same step?
I guess that's true. I was thinking the alcohol could act as a base.
Yep, I can see that. Okay, so I can see how you might be worried about that. That's totally reasonable worry. It turns out, though, that there's no interesting reaction that happens then. The alkene is really not a good enough nucleophile to attack that protonated alcohol even then. So it's true that sometimes the alcohol might get protonated, but then the proton will just fall off a few seconds later. But that's a good thing to think about. So it turns out, so this is not, if you're trying to figure this out from scratch, this would be reasonable. If you've never done this reaction before, it would be reasonable to be super safe by putting them in two separate steps. It turns out, actually, experimentally, though, that it's safe to put in the alcohol at the same time as the acid.
Okay.
So that's not 100% obvious. So the way you were thinking about that was a good one. But we don't really have to worry about the acid protonating the alcohol because there's no interesting reaction that happens after that. So a few seconds later, the proton will just fall off. It wouldn't really change anything. But that's not 100% obvious. So the way you were thinking about that was a good one. So let's go ahead and finish off this reaction.
All right.
Good.
Okay.
Okay, excellent. Let's scroll to the left. So let's try to compare the last three reactions we did. I want us to see the similarities between these. I'll have to zoom out a little bit so we can see the halogen reaction too. We spread these out a little bit. Good. So do you see how these are all very similar to each other? In all three cases, the nucleophile was the alkene. And in all three cases, well, actually I should say, in all three cases we had an alkene and we made it into an electrophile using an acid. But notice we used three different acids, HCl, then H3O+, then H2SO4, and an alcohol. So it's interesting to compare these. The nice thing about H2SO4 is that, remember, hydrogen sulfate won't interfere with the rest of the reaction because it's completely unreactive. Okay, so it might be good to compare these three examples so you can see how you, what type of acid do you use when you want to add a halogen? HCl. What type of acid do you want to use when you want to add water? H3O+. And what type of acid do we use when we want to add an alcohol? Well, then we can add H2SO4 plus the alcohol. Okay, good. So the point here is we're starting to try to get a feel for how to come up with the reagents on our own so that we can fill in the starting materials on synthesis problems or fill in the blank type problems. Now, again, I'm not saying that you can always figure out all of this stuff from scratch. You can see there were some steps here where I had to give you hints or tell you some extra information. So organic chemistry is a mixture of figuring stuff out and memorizing stuff. There are some things here that help to just have memorized, like the fact that we could add the alcohol at the same step as the H2SO4 in the last reaction. That kind of just has to be memorized. So I'm not saying there's no memorization involved, but by understanding the patterns, there's a lot more that we can figure out without just relying on memory for that. Okay, so now we're starting to see how we can use acids and bases to get the reactions we want to happen, so we can start coming up with our starting materials on our own, even if they're not given to us.